this lesson on intermolecular forces. Up until now, we've been talking about intramolecular. Intra means inside, so it's inside the molecule, and these are the bonds that we've been talking about: polar, covalent, etc. So these are the chemical bonds inside. Now we're going to shift gears and talk about intermolecular forces. Intermolecular forces is what holds the individual molecules together. These are the things that that changes from a gas to a liquid and solid. Is what keeps the solid and liquid together. So they're kind of binding forces there. The first of these is the dipole-dipole force. This is when you have a polar molecule and the positive and negative ends of the polar molecule line up. So the positive and negative ends line up, alternating, kind of like a ionic bond. Down here I'm going to do the bonds and little descriptions things. So on ionic, what you have is individual pluses and minuses. Minus, plus, minus. Where the electrons are transferred, and so the charge on these things is plus or minus 1. Plus 1 if they lose an electron, minus 1 if they gain an electron. So that's the charge on the ionic. Dipole-dipole, which would abbreviate DD, is similar, but instead of having separate positives and negatives, you have partial positive and partial negative. Positive and negative. Partial positive lining up with the negative. Partial negative lining up with the positive. And it just keeps on going on and on and on. The main difference between ionic and dipole-dipole is that the electrons are transferred in ionic. Dipole-dipole is just a lopsided electron cloud with one end negative, one end positive. On a scale of plus or minus 1 for a wholly transferred electron, this might be plus or minus, say, 0.3 or so. So it's like a third of the strength of an ionic bond. And when you did the lab where you melted things, you noticed that, where the ionic did not melt and the dipole-dipole did melt. The next type of bond we're going to talk about is a hydrogen bond. A hydrogen bond is a specialized dipole-dipole, so it's between two polar molecules, and specialized if you have a hydrogen, nitrogen bond in it, you'd have a hydrogen oxygen bond in it, you'd have a hydrogen fluoride bond in it. If you have anything like this, where hydrogen is directly combined with the nitrogen, oxygen, or fluorine, these are the highly electronegative atoms. So if it's a hydrogen with a highly electronegative element, and it becomes a very strong bond. And the reasoning for that is if you have, say, carbon has an inner electron shell, and when a very polar, very electronegative element, it pulls the bonding electrons. So the bonding electrons are out here in the second orbit. So when they pull them over, so the electron cloud is here, the nucleus is still covered by the inner shell. Hydrogen, on the other hand, has only the outer shell. So when its bonding electrons are pulled away, the hydrogen proton is more exposed. So the hydrogen's hanging out there. So you got an exposed proton. Because it has it does not have an inner shell. So when its only electron layer is pulled to one side to bond with nitrogen, oxygen, or fluorine, it exposes the proton. The last type is London dispersion force. But a hydrogen bond is abbreviated HB. London dispersion force is abbreviated LDF. It's named after a scientist named London, not the city in England. And this occurs with the non-polar molecules. And in this case, how can they stick together if they don't have a positive or negative end? Well, what happens is they temporarily you have more electrons on one side than the other. One side of the molecule than the other. So temporarily, it's a temporary dipole. You have more electrons on one side than the other, and then that influences its neighbors. So if you have 3 or 4 non-polar molecules lined up, the electron clouds evenly. Well, for some strange reason, say 50 out of 80 electrons just happen to be on one side. This end turns out to be slightly negative. This end tends to be slightly positive. The electrons over here say, hey, there's a positive, let's go look and investigate it. So they start going over. And then the next one say, hey, there's one over here. That one's going back over. And then this one, hey, that one's, so let's get back over there. Now, the problem with this is temporary. By the time you get 4 or 5 down, this is no longer lopsided. It went back to being non-polar. So it happens very temporarily, and it's a very weak bond. So if you have a Lewis diagram, how can you tell which of the 3 intermolecular forces are all 3 of them? Because London dispersion forces occur all the time. You might have more electrons on one side on a polar molecule than you would think. The strength of the bonds, I forgot that. Hydrogen bond, strength of the bond is plus 0.7. That's plus because it's the positive side only. On London dispersion force, on the order of plus or minus plus 1. So dipole, 0.3, plus or minus, and then ionic is 1. So the hydrogen bond is slightly more than double the dipole. London dispersion forces are 10 times weaker than ionic. That's roughly, and those are rough numbers, those aren't exact, but it just gives you an idea. So, what happens if you have a Lewis diagram? You can figure out what it is. Well, you start and ask, is the molecule non-polar? We're going to make a flowchart here. If the answer is yes, then you have London dispersion force, and London dispersion force only. If the answer is no, then you have to ask, is the hydrogen directly on N, O, or F? If the answer is no, then it is both dipole-dipole, because there's no hydrogen, and London dispersion force. London dispersion forces will always occur in all the bonds. The dipole-dipole, it might be, say, 0.3 here, and then it might occur, the electrons happen to jump over there and make it 0.4, or they might pop over the other side and make it 0.2. So there's fluctuations. That's another reason why it's approximations. If it is yes, then you have all three: hydrogen bond, dipole-dipole, and London dispersion force. For example, if you have this molecule, it is nonpolar, therefore it is LDF. If you have this molecule, it has a hydrogen, but that hydrogen is connected to a C again. It's polar, because if you flip it 180 degrees, it's not. So it's polar, and it has a hydrogen, but it's not directly connected to the N. So this is DD and LDF. If it was this molecule, an isomer, where isomer is the same formula, different structure, now the H is directly connected to the end, and you have hydrogen bond, DD, and LDF, all three of them occurring. This ends this lesson on intermolecular forces.